volume of solids of revolutions, it's not always advantageous to take the slices in the plane region perpendicular to the axis of revolution. Sometimes it's just impossible actually to be able to set up the integral for the volume if you do it that way. Well then, what if we took our subrectangle representation in the plane region parallel to the axis of revolution? Well, if we do that, we're doing something called the shell method. And the shell method is used when the subrectangles in the plane region are parallel to the axis of revolution. Now in doing that, we actually get a different figure of each of the little representation sort of slices. And it actually will give us then a different type of a volume. So imagine if I have this region that is bounded by this y equal x to the fifth plus x plus 1 curve, y equals 0, which is the x-axis, over the interval from 0 to 1. So this region represented by the shading that I'm doing, and I'm revolving this around the y-axis. If I take my subrectangle representation in the plane region perpendicular to it, like I did with the disc or the washer method, then these would be horizontal. And horizontal subrectangles would have to be dy. Now if I set up and did this dy, then I would have to have my equation as x equal an expression in y. And this y equal x to the fifth plus x plus 1 is almost impossible to solve for x in terms of y. So it's not advantageous to run my subrectangles perpendicular to the axis of revolution for this particular problem. The other region that would be hard with it is that I have not the same situation throughout. I have from the y-axis to 1, from the y values to 0 to 1, and then after that I have 1 minus the curve. And that's where that solving the expression x equal to an expression of y's would have to occur if I ran them horizontal and I was dying it. So I need to dx it, which means I need to run my subrectangles vertical, but my axis of revolution is vertical, so they are actually running parallel to the axis of revolution instead of perpendicular to it. So this is kind of like that zero gravity ride at the carnival, where you're sitting there and it's spinning and you have just that shell. Well, if I take a subrectangle representation in the plane region, and I think of those being worked across the interval that we're revolving, then for each of these, they have this very thin little thickness of my dx. And as I spin that around, I get a cylindrical shell. Now, thinking about taking that cylindrical shell and opening it up, I would want the area of the rectangle that's formed. Well, the height of the rectangle is the height of your little subrectangles throughout the interval. That's that h of x. And the length of your subrectangle that's cut and opened up throughout is the circumference of the circle when it was enclosed. Remember, the circumference of a circle is 2 pi r. So 2 pi is what I have as a constant factor out in front. And this rho of x or rho of y, whichever case we have, is the radius that reaches from the axis of revolution out to those subrectangles. So it has to work its way across the span that you have. So our volume formula for the cylindrical shell method is the volume is equal to 2 pi times the integral from c to d of rho of y, h of y dy, or 2 pi times the integral from a to b of rho of x times h of x dx, whichever the representations have to be, whether they're vertical for the dx or if they're horizontal if you have a horizontal axis for the dy. Rho of x is your radius from your axis of revolution out to the shells as you work across the region, and h of x is the height of those cylindrical shells as you go across the region. So let's look at this example specifically. I have find the volume of the solid formed by revolving y equal x to the fifth plus x plus 1, y equals 0 on the interval from 0 to 1, bounded by that, about the y-axis. So this is my y equal 1 is, or sorry, y equals 0 is the x-axis over the span from 0 to 1, so this is x equal 1, and my green curve here is y equal x to the fifth plus x plus 1. So we've discussed why we would want to run our subrectangles vertical. I also have consistency throughout the interval that the curve, the green curve, y equal x to the fifth plus x plus 1 is on the top, and the x-axis is on the bottom throughout the entire curve. And it's an expression in x's, so I want to dx it. So I want my subrectangles to be vertical, but then that makes them parallel to the axis of revolution, so I need to do the cylindrical shell method. My volume then is 2 pi times the integral from 0 to 1, thinking about having those shells across that interval, of rho of x is the radius reaching from the axis of revolution to the cylindrical shells, that radius. And that's just the horizontal movement, and the horizontal movement from the y-axis over is just the x coordinate. Its representation is then just x. And then my height of my subrectangles, this region is tight against the x-axis, so it goes from the x-axis up to the curve throughout. So the height is my x to the fifth plus x plus 1. And then dx is the little thickness of those cylindrical shells. So now that we've set it up, we're going to take and distribute the x through so that we can get ready to integrate it. So that was just distributing our x factor through. So our volume is 2 pi times the antiderivative of x to the sixth plus x squared plus x is my 1/7 x to the seventh plus 1/3 x cubed plus 1/2 x squared. And we are evaluating that from 0 to 1. So put in the 1. Minus, put in the 0. And then looking at our evaluation, that's 2 pi times, well, this is just going to be 1/7 plus 1/3 plus 1/2. So that's 41 over 42 because it's minus 0. And then 2 pi times my 41 over 42. My volume is, there's a common factor of 2, top and bottom. So I have 41 pi over 21. So my volume is 41 pi over 21 cubic units.